Welcome to the third unit, which is stability analysis and root locus technique. So here we have the concept of bounded signals. So supposing I am showing three signals x1t, x2t, x3t. The first one actually is bounded, so which means it is not either going to minus infinity or plus infinity. It starts at 1 and decays back to 0. Likewise, supposing I have a signal x2t, it is bounded, so it is having a value 1. Similarly, supposing I have a signal x3t, even though it's a sine wave, even though it is oscillating in different directions, it is bounded within the bounds minus a and a. On the other hand, if I show a signal x4t, this is exponentially increasing or exponentially decreasing, going up to either plus infinity or minus infinity. So this is an unbounded signal. Likewise, supposing I have a signal x5t, then this is continuously increasing. So this is an unbounded signal. So we have a concept called bounded input, bounded output stability. In this particular thing, supposing there is a stable system and I give it a bounded input, I will get a bounded output. Supposing there is an unstable system, to this system, supposing I give a bounded input, I will get an unbounded output. Now let us consider a system with a transfer function g of s with r of t as the input and c of t as the output. C of s here is given by g of s into r of s. Now multiplication in the frequency domain is equal to convolution in the time domain. So c of t is equal to 0 to infinity g of tau r of t minus tau. Now what we are saying is r of t is bounded, so absolute value of r of t is less than or equal to m is less than infinity. If this is the case, what happens is absolute value of c of t is equal to absolute value of integral 0 to infinity g of tau r of t minus tau d tau. From Schwarz inequality, this is less than or equal to integral from 0 to infinity absolute value of g of tau, absolute value of r of t minus tau, d tau. Now r of t minus tau is nothing but a time shifted version of r of t, and the bounds don't change, so this is bounded to a value of m. So this is less than or equal to m integral 0 to infinity absolute value of g of tau d tau. So what we learn from here is the output absolute value of c of t is bounded when integral 0 to infinity absolute value of g of tau d tau is less than infinity. So now we come to what is called as a routh-hurwitz criteria. What we saw was whenever we had a first order system or a second order system, it was very easy to find out whether the roots were lying on the right hand side of the S plane. As the transfer function gets more complex, it becomes very difficult to solve the Routh array. So generally, we use what is called as the routh-hurwitz criteria. This method involves two steps. First, generating the Routh array. Second thing is interpreting the Routh array for location of poles and zeros in the S plane. Let us consider as a simple characteristic equation of the form q of s is equal to a n s raised to power n, a of n minus 1 s raised to power n minus 1, a of n minus 2 s raised to power n minus 2, a of n minus 3 a raised to power s minus 3, and so on, a1s plus a0. Here we can write a Routh array like s of n minus 1, s of n minus 2, s of n minus 3, and so on up to s of 0. Now take alternate coefficients in the first row. So you have an minus 2, an minus 4, and so on. In the second row, you take the coefficients which you left out previously. So you have an minus 1, an minus 3, an minus 5, and so on. So here what we use is, we use some kind of a method to find out third row, fourth row, and finally complete the Routh array. So how do we get b of n minus 1? B of n minus 1 should be equal to a of n minus 1 into a of n minus 2 minus a of n into a of n minus 3 by of a of n minus 1. B of n minus 2 is equal to a of n minus 1 into a of n minus 4 minus a of n into a of n minus 5 by a of n minus 1. Likewise, we can calculate c of n minus 1. c of n minus 2 and so on, and the process is continued till you get s raised to power 0. Now consider a particular example. C of s by r of s is 10 by s raised to power 6, 2s raised to power 5, 2s raised to power 4, 3s cube, 5s square plus 6s plus 1. See, the characteristic equation is always the equation in the denominator. So you get s raised to power 6, 2s raised to power 5, 2s raised to power 4, 3s cube, 5s square, 6s plus 1. So for generating the root array, we take alternate coefficients. So you can get the first row coefficients and the second row coefficients. So by selecting the first row and second row coefficients, you can fill up the root array as shown. Now for calculating the first value, you have 2 into 2, 4 minus 3 by 2, which is 0.5. Likewise, you have 2 into 5 minus 1 into by 0.5, which is 2. So likewise, you can complete all the elements of the root array. Now for the system to be stable, there should be no change in sign in the first column. But supposing you look at the first column of the root array, from 1 to 2 there is no sign change, from 2 to 2.5 there is no sign change, from 0.5 to minus 5 there is one sign change, from minus 5 to 11 by 5 there is one sign change, and likewise, so there are two sign changes. So there are two roots on the right hand side of the S plane. Now we consider some special cases of Routh criteria. One, when the root array becomes 0 in the first column of a row, and second, when the root array sometimes may have all zeros in the entire row. Whenever we have a 0 in the first column, let us take another example. S5, 2s4, 3s cube, 6s square, 5s plus 3. Again, you form the first row coefficients and the second row coefficients and form the Routh table. But here what happens is 2 into 3 minus 6 into 1, this becomes 0. Again, 2 into 5 minus 3 into 1 by 2 is 7 by 2. So one element in the first column has become 0. So now what you do is you replace it with something called epsilon, an infinitesimally small value, and you continue with your calculation. If you really do this, what you will find is the third row becomes epsilon and 7 by 2. Fourth row becomes 6 epsilon minus 7 by epsilon 3. The fifth row becomes 42 epsilon minus 49 minus 6 epsilon square by 12 epsilon minus 14. And the last row becomes 300. Now to find out the sign, you take limit of 6 epsilon minus 7 by epsilon, which can be written as limit of epsilon tending to 0, 6 minus 7 by epsilon. So this tends to minus infinity. If you take the limit of 42 epsilon minus 49 minus 6 epsilon by 12 epsilon minus 14, it will tend to 49 by 14, which is a positive number. Now if you really take all the elements in the first row, what you will see is from 1 to 2 there is no sign change, from 2 to epsilon there is no sign change, from epsilon to 6 epsilon minus 7 by epsilon you have one sign change because it tends to minus infinity. From this to the next one, which is 49 by 14, there is one sign change. So there are two sign changes. So there are two poles lying on the right hand side of the S plane. So the system is unstable. Now you consider the case 2 when all elements in the Routh array become 0. So supposing you have the Routh array as shown and you have 1, 2 and 4 in S4 column and in S3 column all become 0. So you need to take what is called as an auxiliary equation. An auxiliary equation is given by S4 plus 2S square plus 4 is equal to 0. Now you should be able to take a derivative of A of S to get dA of S by ds, which is 4s cube plus 4s equals to 0. So for convenience, you can divide the coefficients by 4. So you have s cube plus s is equal to 0. So now all the coefficients which were now 0 are replaced with the values of the coefficients of the derivative, which is 1, 1, 0. So what you can do is you can take one kind of an example here, which is s cube plus 5s square plus 6s plus 30. So what you can do is find the first row coefficients and the second row coefficients and find out the root array. So you have s cube, s square, s1 and s0. For s cube you have 1 and 6. For s square you have 5 and 30. The moment you calculate this, what you'll find is 6 into 5 is 30 minus 30 by 5, which is 0. The second column, the second element in the row has also become 0. This is of the form 0 by 0. So now you need to take an auxiliary equation, 5s square plus 30. If you take dA by ds, you are going to get 10s plus 0. So what you do is you replace this by 10. So now if you do have the third row as 10 and 0, what you will find is 10 into 30, 300 minus 5 into 0 by 10, which is 30. And now what you will find is all elements of the first column have the same sign. But now that you have used an auxiliary equation, it shows that there are roots on the j omega axis, hence the system is limitedly stable. Take the next one. Pfs is equal to s5 plus 2s4 plus 2s cube plus 4s square plus s plus 2. Here again you find the first row coefficients and the second row coefficients, and then you form the root array. Here you will find that 1, 2 and 1 is in the first row, 2, 4, 2 is the second row. The moment you calculate 2 into 2 minus 4 into 1 by 2, you will find that the entire row becoming 0. So you take the auxiliary equation 2s4 plus 4s square plus 2 is equal to 0, and then you take a derivative of that. So AFS is s4 plus 2s square plus 1 is equal to 0. dA by ds is equal to 4s cube plus 4s plus, so s cube plus s is equal to 0. So you replace the row with zeros of the coefficients of dA by ds. So you're going to get 1 and 1 there. But if you again do, you're going to get zeros for the first one. So you again take an auxiliary equation, replace the rows of zeros by coefficients of dA star by ds. Now if you see, there is no change in sign in the first column. However, the roots plus j minus j plus j minus j, there are 4 roots lying on the j omega axis. Remaining 1 root is in the left hand of the s-plane. The roots of the auxiliary equation are the roots of the characteristic equation. Here repeated roots are there on the j omega axis. Hence the system is unstable. Take another example. Using routh-hurwitz criteria, determine the stability of a closed loop system having the following characteristic equation. Determine the number of roots of each equation that are on the right hand plane of the j omega axis. So I have s4, 2s cube, 10s square, 20s plus 5. So you can find out the first row coefficients and the second row coefficients and get a root array. Here again what you will find is 2 into 10 minus 20 into 1 by 2. You get a 0. So you replace it with an epsilon. So what you do is the next element would be 20 epsilon minus 10 by epsilon, and the next element would be 5. If you really see the sign of elements in the first column, what you will see is S1 tends to minus infinity. So there are 2 sign changes, which means 2 roots are on the right hand side of the S-plane. Hence the system is unstable. Take another equation, S5 plus S4 plus 3s cube 9s square plus 16s plus 10. Form the root equation. What you will find is there is one sign change in the s cube thing and there is one more sign change in the s square thing. So there are 2 sign changes. So system is on the right hand side of the S-plane. System is unstable. Now take another form of problems where what you have is you have a characteristic equation of the form s4 plus 25s cube plus 15s square plus 20s plus k. So for each of the characteristic equations of the feedback control system, determine the range of k for stability. Determine the value of k so that the system is marginally stable, and find the frequency of sustained oscillations.